Welcome to Phys 501, Lecture 2, Facilitated Diffusion and Active Transport. This lecture was taught by Dr. El Teat on August 21st of 2015. Let's get started. Simple diffusion is a passive transport mechanism, does not use any type of metabolic energy. We covered dissolution model and microporous model. The dissolution model the dissolution model is for diffusion that occurs through the bilayer. So you will see that you don't need any protein channels for this. However, microporous model for this, you are taking into account these protein channels. So if you look at the differences, it's negative dk delta C over delta X, dk, these two being diffusion coefficient and partition coefficient, and delta X is the membrane thickness. These three terms can be combined as P, which is permeability, and you should remember that the units for permeability is centimeter over second. And the same thing can happen for the microporous model. So JS, the solute flux, which is negative N over A, pi A squared D, delta C over delta X, you can combine the terms that are encircled as P. You should also remember that the negative sign also gets combined as P. And P is, again, permeability. So here, again, we're just emphasizing the fact that JS, think of this as Y, P as your slope, and delta C as X. So it's Y equals AX. And what this means is that the higher the concentration difference, the higher the JS, the higher the flux of solute. And P is here. You can see it as the slope. And P is always, again, positive. All right, next slide. Facilitated diffusion. So here, we're seeing that facilitated diffusion has a few very unique characteristics. It shows specificity. It doesn't just let in anything. It shows competition with chemicals of similar structure. This means that if you have a similar molecule, it will show signs of competition. A prime example being, I was thinking of a receptor. Later in GI, you will learn that CCK and gastrin, they are similar and they compete against one another. So again, if you have a channel for, let's say a cation A, it will show competition with another cation of similar structure. And it's saturable. If it's working full time and it's transporting as much as possible, then of course it's not going to be able to transport any more than that. And you can see from the graph that it reaches a certain threshold and it can't go any higher. Whereas passive diffusion, the higher the solute concentration, the higher the solute flux. So let's see. When you look at this equation, QS equals Qmax times S over Km plus S. This equation is how you get a graph that looks like this, increasing in a linear fashion in the earlier part, and then kind of just approaching a threshold towards higher S values. The reason this happens is because if this S is very small, then you can ignore this term right here. Then what does it become? It just becomes Qmax times S over Km. That's kind of like Y equals constant times some variable. So you're going to get a line that increases. And now look at, think about this equation when S's value is higher. Then when S value is super high, then it kind of becomes Q max times S over S. This Km becomes insignificant. So Qs equals Q max times S over S, which just becomes Q max. And that's why you get Qs, this Q transport, equaling this Q max. And that's this dotted line up here. So again, when S is small, you can ignore this term. Therefore, it's Q max times S over Km. When S is huge, you can ignore Km. And that's why it just becomes Q max, because S's will cancel out. So it's going to approach Q max. That's how it works. And for passive diffusion, the higher the delta C, the higher the Js. That's kind of from last lecture. Now, this is showing you that a good example of glucose transport in the erythrocyte membrane of glucose uniporter. And that is a prime example of a facilitated diffusion. They do show saturation, and when you have a facilitated diffusion, it doesn't always obey the equation Js equals P times delta C. Next slide. Okay, facilitated diffusion. So this is kind of illustrating the mechanism of facilitated diffusion, and you can kind of think of it as an enzyme. And the reason you can think of it as an enzyme is because when you have your solute on the left side going into an enzyme that accepts solutes from the left side, it can go in, and then once it's bound, and this dot is showing you that the solute on the left side is bound to the enzyme, and then it'll change its conformation, and it will let out the solute, which is now on the right side. So that's what SR is showing. And then the enzyme that is open to the right side will change its conformation and go back to EL. And this figure is written with variables expressed as variables here. So the sum is that you move the solute that used to be on the left side to the right side, and that's what a facilitated diffusion uniporter is doing. So just like in any catalytic reaction, it speeds up the process. It goes along the gradient, and it's not part of the net reaction, of course. All right, so where does it get the energy to move things? Well, there is energy in the imbalance of concentration. So you have mu R and mu L. So remember, mu naught, these are the electrochemical potential at the standard conditions. And then you have RT, ln, concentration right and concentration left, joules per mole. So this is showing you energy. When you multiply mu R and mu L with the number of moles, then you get delta G, which is free energy. And when you subtract one from another, you get delta G. And what the delta G shows you is it shows you the capacity to do work. So when it's negative like this is showing you that it'll go from left to right. And don't try to figure this out mathematically. Just think about it in terms of what will happen when you have imbalance of concentration. CL being greater than CR, that's going to give you a negative value because you're going to have some fraction. If you draw a logarithmic graph, ln of 1 is always at 0, and a value less than that will always give you some negative value, and a value greater than that will give you some positive value. So when it's negative, it's going to be negative, and when delta G is negative, you know that it can do work. And that work is going to be from high concentration to low concentration. It's just a mathematical way of expressing that. And when right side concentration is higher, it's obviously going to go to the left. And mathematically, it will show that the opposite is going to happen if you keep things this way. And when you get ln of 1, that's just saying CR and CL are equal, and that's when you're going to get 0. So you're at equilibrium. There is no net flux. In a passive diffusion, obviously, you're not using energy. Therefore, it goes along the gradient. And here we are assuming that it's an uncharged solute. So we don't have to take into account the electro part of electrochemical gradient difference. Ions can be passively transported across membranes by ionophores or channels. And ionophores, you will learn some examples here. And then these are the channel formers. I memorized these. I don't think they were on the exam, but I did memorize them. And valinomycin and gramicidin, you will see these again later in biochem, so you might as well get familiar with these terms. Fungi and bacteria make a class of poison called ionophores, and the reason these are poisons is because it screws with other bacteria's ion gradients. So, for example, if you're a bacteria, you're trying to maintain that ion concentration difference. So you don't want hydrogen ions, for example, coming inside your cell, but these ionophores, they can transport potassium ions, for example. I think some of them can even mess with your hydrogen ion concentration. So that's why it's a poison. It's a mechanism for fungi and bacteria to kill other bacteria. Ionophores can be carriers or channel formers. I think that's important. So channel formers are here in the bottom, and carriers are up here. Carriers, these are little bags that can contain an ion, and it will carry it to the other side and let it out, and it'll go back and rinse and repeat. Whereas channel formers, these two monomers will come together across the bilayer and it'll form a channel. And that's the difference. Ion channels can be either voltage gated or ligand gated. And that's really important. Voltage gated channels are sensitive to, just like it says in the name, voltage difference. So depolarization, for example, can trigger voltage gated channels. Ligand gated channels, these have to have the correct ligand bound to its receptor site, and then it will open or close. So that's the difference. Voltage gated channels usually have a charged amino acid on close to the cytosol or the lumen side, and then the change in voltage will push or pull these helices or beta sheets, and then that can change the conformation and it'll open or close. And ligand gated, again, these will also have a ligand binding site, and then that will open or close these channels. So be familiar with these. Ligand gated ion channels, here are some examples. Nicotinic acetylcholine receptor, that is pretty much how your nerves talk to each other. And then you've got these other examples. I can't remember if I memorized these or not, but I don't think they were on the exam. And then you have ion gated ion channels. So these are activated. It says in the name that it's activated by an ion, and it lets ions in and out. And then you have voltage gated ion channels, and you'll have voltage gated sodium, calcium, and potassium channels. So in what direction does a charged particle move? So do you guys remember the Nernst equation? This is from last lecture. So it'll come back. And current is equal to coulombs per second, and its unit is ampere. That is how you measure current. So if you remember from Nernst potential, Nernst equation, this tells you the voltage you need in order to have zero flux given the concentration difference inside and outside, or left and right. So here, RTZF, these are just constants, or for Z, that is the valence number of the ion. So it can be like +1, +2, -1, something like that. And here, the I, so this is just like V equals IR. Here's your V, the driving force, that's the voltage, and I is the current, and it's V equals IR, and they move the R to the right-hand side. And 1 over R is such a hassle to refer to that they just changed 1 over R as G. And G is cord conductance. And G is just literally 1 over R. And G is always a positive number because resistance, if you think about it, cannot be a negative number, right? So this slide has a typo, if I believe. So here, let me just go through this. So what this is trying to show, this is where the typo is. The left-hand side, the right-hand side, if EM is less than EX, actually. Excuse me. So if EM is less than EX here, then you will have a negative current. So let me go over this. A positive ion leaving the cell is a positive current. A positive ion leaving a cell is positive current. So EM here, that's the membrane potential, and EX is the equilibrium potential. And if the membrane potential is less than EX, then you'll have a negative current. And that's because you see a positive ion coming in, and that's what it's showing, that it's a negative current. If they're equal, nothing happens. That's easy. Let's look at this example. If EM is greater than EX, so the equilibrium potential is, let's say, +60, and the membrane potential is something greater than that, then it will push out positive ions. So like I said, positive ions leaving the cell is a positive current. It's just good to memorize that. So from the right to left, positive ions are leaving, and that's because EM is greater than EX. EM less than EX, then you'll have a negative current. So I'm going to switch to the other PowerPoint. This slide fixes the typo, and this is the slide that we had. So here, this is where it's incorrect. So this is a pretty, I didn't think it was that easy to understand this graph. So here we go. An outward current, which I explained is positive ion leaving, that's your positive current. So what's important to understand is that these two intersections right here and here, these tell you exactly the potential you need. So VM is your potential and I is your current. So if you have CI greater than CE, that's showing you that the concentration of cations inside is greater than outside, intracellular, extracellular. So if it's greater on the inside and less on the outside, you obviously need some negative potential to trap those higher concentration of cations from leaving. Does that make sense? So imagine I have a lipid bilayer and I'm inside the cell. If I have 100 cations inside and let's say 20 cations outside, I need some negative membrane potential. I need a negative equilibrium potential to prevent the cations inside from leaving. That's how I'm going to maintain my equilibrium potential. That's why this is negative. Ci is greater than Ce. You have more cations inside. And that's why you need a negative membrane potential, a negative equilibrium potential, to have I of 0. So here E is reversal potential or equilibrium potential. Once you go past all the way here, this is so negative that you can actually start pulling in cations. Isn't that crazy? I thought it was crazy. All right. So as you go to the right, as you lose this negativeness, you start to have a positive current. Cations are going to be leaving. And then up here, it just becomes a V equals IR relationship. Now out here, this red line, Ci is now less than Ce. Now, that's telling you that you have more cations outside than inside. When you have more cations outside than inside, you need a positive Vm to keep those cations from coming in. Makes sense, right? If I'm a lipid bilayer, I'm a cell, and there's a lipid bilayer, and there are 100 cations outside, and there are 20 cations inside, I'm obviously going to need a positive reversal potential or equilibrium potential to have a flux of 0. And that's how you're going to get I of 0. So that's what this graph is showing you. And as you go to the left, you will see that you can start pulling in cations. Therefore, you're going to have an inward current of cations. You're not able to keep those out anymore. So you're going to have a flux of cations inward, and that's why you see a negative I. And if you make the membrane potential very, very positive, then you're going to start pushing the cations inside the cell to the outside of the cell. And that's how you're going to get positive I. That's a pretty extreme situation. So here it says this is a typo. For a negative ion, it is just the opposite. That's true. An inward current is, okay, so let's go to the other PowerPoint. An outward current is negative, right? Because an outward current of a cation was a positive current. So if it's just the opposite, an outward current of an anion is going to be negative. That's how you get an opposite statement. An inward movement of an anion is going to be positive. Just write it down and switch one word, and that's the opposite statement. So, like I said, a cation leaving the cell is a positive current. Positive leaving is positive. Cool? Yeah. Okay. Let's go to the other PowerPoint. Okay. Here we go. Math. We have to be able to do math because you will see math questions. If sodium channels are suddenly opened in the plasma membrane, do you expect an inward or outward current? If you kind of think about this, you will always have an inward current, because if you remember from first lecture, you always have higher concentration of sodium outside, and if you open up your channels, they're going to rush in. So here they give you some parameters. Sodium inside is 4 millimolar, outside 140, and EM is negative 80. So you take the Nernst potential equation, and then let's do the math. Negative RT over ZF times ln of CI over CE. And they did the math for you, which is convenient. Then you get negative 26.7 times negative 3.56. And I really highly recommend that you do this math yourself, because if you never practice doing these types of math questions, you will freak out during the exam. So don't do that. Then you get plus 95 millivolts. Cool. Now, remember from the previous slide, I equals right here, gx times em minus ex. We're going to do that. So your em is negative 80. And then your ENA, the Nernst potential that you calculated, is plus 95. When you subtract that from negative 80, you will get negative 175 times conductance, GNA. GNA is always a positive number, so I is negative, and in order for I to be negative, it has to be cation coming in or an ion leaving. But we're talking about a cation, so it's going to be inward and it's going to be a negative current. And if you think about this, this is a huge number. Like the membrane potential is negative 80 and the equilibrium potential is negative 85. Whoops, what did I just say? The membrane potential is negative 80 and then the equilibrium potential is plus 95. What this is showing you is that you need plus 95 to keep the cations, the sodium ions, from coming in, right? You have so much more sodium ions out there than inside. And when you have plus 95, you can stop this flux. You can stop the cations from coming in. But what are you at right now? You're negative 80. So we want to be at plus 95, but you're at negative 80, then bam, you're going to have a huge influx when the channel is open. And this is how your muscles and your nerves communicate, which is really cool. Okay, so are they still doing the math? Yes. Plus 95, you got negative 175 GNA, and the negative is telling you that it's going to be a negative current, cations coming in. So at which EM, the I and A will be 0, and the answer to that is going to be plus 95. That's the definition of Nernst potential. If your membrane potential is greater than 95, you'll have an outward current. Remember, the definition of outward current is cations leaving, positive leaving is positive. So that's how you're going to get a positive, an outward current. Bam. Right there. So there's a homework question, and I'm going to go over this at the end of the PowerPoint. So yeah, I'm going to go over this homework question after I finish the PowerPoint slides from the lecture. In resting conditions, the sodium conductance in cells is low, and that is a true statement. The conductance is going to be low, meaning the resistance is very high. Your sodium ions can't just come in, right? Your lipid bilayer is a very hydrophobic layer, so sodium ion is not going to be able to come in. So when you have this high concentration of sodium ion outside, it is a form of energy. You're going to be able to open these channels and ions are going to be able to come in. Water moves through aquaporins. It's a porin. These are little channels, pores. And aqua means water. So, yep, you can use aquaporins to move water. The difference between passive and active transport. I mean, you've got to know this. So passive does not use energy. It is and that's the only distinction. Do you use energy or do you not use energy? That is how you determine whether something is a passive transport or an active transport. So active transport cannot occur spontaneously. You need energy. And you can move things against the gradient. For passive transport, the energy just comes from the solution itself. I forget whether this was a question on the exam. I feel like it may have been, or maybe someone just asked me and I got it right. I don't know. And it always flows along the electrochemical gradient. So remember that too. All right, so under active transport, you have two different types of transport. One is a primary and the other one is a secondary. Under primary, you have sodium, potassium ATPase, calcium ATPase, and hydrogen ATPase. And you can already see that when you have something A, when it ends with the letter A, it's very highly likely that it's a primary active transport. So sodium potassium ATPase, you've probably seen this before. Calcium ATPase, you got the PMCA and SERCA, plasma membrane calcium ATPase, and smooth endoplasmic reticulum ATPase. So these, therefore, your calciums. And then you got your hydrogen ATPase. And the difference between primary and secondary is that you directly use ATP hydrolysis to move your ions. So it's the phosphorylation and dephosphorylation that drives this. As for secondary, you're going to use it indirectly. You're going to use ATP's hydrolysis energy indirectly. So you're often using some other ion gradient to move your solute of interest. So here we see that we have a sodium glucose cotransport. So you concentrate your sodium ion concentration, and then so you have a lot of sodium ion like on the outside, which is often the case, and then you're going to use that to co-transport glucose. When you have, for this, NCX, when you have X in it, it's probably an exchange, and that's going to be an antiport. So in this case, co-transport, that's a symport. And when you have an exchange, that's an antiport, meaning symports, they come in together, and antiport, they exchange. One comes in, one goes outside. So NCX case, that's going to be sodium coming in and calcium leaving. Examples of primary transport. Here we go. Gastric hydrogen ATPase. I don't think you have to memorize details. Again, I'm not the one making the test questions. I just memorized all these little details, but you probably don't have to. Omeprazole is a very famous drug. It's what you take when you have heartburns, right? And then sodium potassium ATPase, PMCA, SERCA, vesicular hydrogen ATPase. Again, these are all primary active transports. That's probably the important thing to remember, that these are primary active transports. And again, as you notice, they all have the letter A in it. ATPase, A, and A. So do remember that. The sodium potassium ATPase here, we push 3 sodium ions outside and we bring in 2 potassium ions inside. And then you use an ATP. So we can see the concentration difference here and here, the membrane potential of -80. The cycle is electrogenic, meaning you generate an electrical difference. So the outside is going to become more positive, and the negative as a result becomes more negative. But it's actually not the sodium potassium ATPase that creates this electrical gradient. We're gonna go over that later. All right, so this is a lot of math. But the take-home message is that it's actually quite simple. Let me just explain it. You got the ATPs being hydrolyzed, right? And then 3 sodium ions inside, I, going outside. K, in outside, coming inside, right? So we all seen this before. So what is happening down here? Well, what's happening is that we broke it down to the individual components. So ATP being hydrolyzed, sodium coming from inside to outside, and potassium going from outside to inside. And then we calculated their associated, the free energy difference. So it's not free energy yet because we haven't multiplied the number of moles yet. So for the ATP hydrolysis, you got -57.1. And for sodium, again, remember you're going against the gradient. So inside versus outside. Now, Don't follow that. Try doing this. Think about the sign you will need. If you're moving something from inside to outside, that's work, right? You're trying to herd cats, for example. If you have a lot of cats inside a small space and you need to bring in more cats into that small space, bringing in more cats without letting the cats inside leave that small space is going to be difficult. The same concept applies. You've got lots of sodium outside and you're outside and you're trying to push out more sodium to the outside. That's hard work. So that's why it's going to be positive. So if you're not getting some positive value, that's probably wrong. That's why this happens. And then RTLN, again, you're moving potassium ions high inside, low outside. So again, you're going to get a positive value. And then as for the F value here, the F times negative 0.08, you are thinking from the perspective from the final destination. So because you are on the outside, ultimately, that's why it's going to be positive here. And as for the potassium, your final destination is inside. That's why it's going to be negative. So when you take all these values and you add them all up, you have to multiply sodium, because you have 3 of these, by 3. And as for potassium, you have 2, so you got to multiply by 2. And when you add it all up, you get negative 11 point something something. And the negative delta G tells you that the reaction will occur simultaneously. And that energy comes from the ATP's hydrolysis. So here you will learn some secondary active transport mechanisms, the antiport exchangers. So you have the X and EE, exchange. And you will learn like every one of these later in the course, either biochem or histo or physiology. 1 calcium leaving, 3 sodium ions coming in. Bicarbonate exchange, and sodium hydrogen exchange. Here you got the symports, sodium ions and amino acids, sodium ions and iodide, and sodium glucose, LT, SGLT. So yeah, these are all examples of antiports and symports. So as for the NCX exchange, we're going to be doing the same math that we did for the sodium potassium ATPase. NCX is important to reestablish low intracellular NCX is important to reestablish low intracellular calcium concentration. So this is true. Calcium ions, you don't want, I shouldn't say you don't want. Calcium ions intracellularly is a method of signal. So you don't want this value. You want to be able to control this value. So NCX, this allows you to use high sodium concentration outside to drive out calcium ions. So they're going to come in and you're going to push calcium ions to the outside. And remember, calcium ion concentration outside is very high and it's in the nanomolar range for inside. So 3 ions come in and 1 calcium ion goes out. As you can see, it is electrogenic and it's an antiport. And this is a secondary active transport. So it's just saying that you have a electrogenic movement, and it can revert in physiological conditions, because if you think about it, if you have pretty high sodium ion concentration inside and high calcium inside, then it can like work backwards. So in certain physiological conditions, it can be reversed. And this is the math. Again, we're doing the same thing that we did before. Here is the entire equation. You break it down into their individual components. And then if you add it all up, you'll get a negative value. And the negative value signifies that yes, this reaction can occur spontaneously. So let's go over that homework question. Where is it? Here. So the homework question, calcium ion inside is very low. It's very high on the outside. Again, be careful with these units. I do believe you have to be able to convert between like micro and milli. And the Z for calcium is going to be +2. Do not forget that. Okay, negative RT over ZF, ln of CI over CE. So you're going to be given these values, or the professor might give you like negative RT over F is this value. Do the math, and then you will get plus 126. It's actually not a bad idea to memorize these common equilibrium potential values for a few important ions like sodium, potassium, and calcium. So sodium, if you remember, is like plus somewhere between like 60 and 80, right? 95 was it maybe? I think it was 95. And then for calcium, it's plus 126. So you take this value and then you do the EM minus ECA. EM is negative 80, ECA 125. So you get negative 205. And that's pretty high, right? So when you have calcium ions coming in, when the calcium channels open, calcium's Nernst potential is 125, 126, right? But the membrane potential is negative 80. So it's going to go from negative 80 all the way up to plus 126, right? And that's a lot of driving force. And that's why you get this humongous value. Now, I have the bottom portion cut off. So it reads, if EM is negative 80, ICA should be inward in these ionic conditions. And yes, that's true. When you have a membrane potential of negative 80, you're going to have cations coming in. And as I emphasized, positive ions coming in is negative current. So try practicing these questions and you should be in good shape. Also, there's a extra slide that the professor gave out. Trying to make the size work. Okay, so some students were asking why in here you have this negative and why in this equation you do not have the negative. So the reason you have a negative in front of the Nernst for the Nernst equation is because we calculated electrochemical potential for right side and left side, inside and outside the cell, and then we subtracted them. Remember the definition. It is the voltage you need in order to have zero flux, right? And one thing we assumed was that this psi r minus psi l is 0. And the negative sign tells you that when the magnitudes are equal, but the sign is different, you get an equilibrium, so nothing flows. But the delta G equaling nRT ln Cr over Cl, this is representing the chemical potential energy that's there. You have an inherent energy built into concentration gradient, when you have, let's say, these, like, I don't know, if you make a humongous pile of Lego blocks on the left side, and when you push that over, that is a form of, it's a potential energy. It is a form of energy that you can harness from, right? And that's what this is showing you. The NRT-LN-CrCl is representing the free energy that can be harnessed from chemical gradient, and that's why you don't see the negative sign in it. All right, so when you have the solute concentration difference, you can get energy out of it, and that's why you don't see the negative sign. Whereas in the Nernst equation, here you are assuming that you have zero flux and you need equal but opposite force to stop, to prevent any flux. And that's it for the second lecture. I hope you enjoyed it. All right, I will see you guys tomorrow, or maybe sometime later. Goodbye.